All right, good morning, boys and girls, and welcome back. Picking up where we left off with volumes of solids revolved around the x-axis. We talked about the disk method, and we did a few problems. And we left off with this one right here, where we did y equals 4 minus x squared. X equals 0 and y equals 0, and revolve that around the x-axis. All right, we're going to just modify this last problem a little bit now. All right? And we're going to deal with y equals 4 minus x squared still. But now we're going to deal with the region bounded by x equals 0, the y-axis, and the line y equals 3. So this will change things just a little bit. All right, so 4 minus x squared is still this parabola that's opening down here, and y equals 3 is the horizontal line at 3. And so if we look now, what we're really talking about is this region right in here. Just erase that real fast, and so we're going to revolve this shape here now around the x-axis. All right, and now when we do that, because we have this gap, if you look at a cross-section of this, it's going to look something kind of like this, where instead of getting a disc now, we're going to get a washer. Like nuts, bolts, and washers, you're going to get a washer, like a donut-looking shape. From the outside of the shape is going to create part of the circle, and then the inside part is going to create a circle. All right? If we look at the cross-section, it's going to look kind of more like that right there. All right? Let me take you back to our app website, and let's see if we can look at what this is going to look like in 3D. All right, so here we have our two functions. We have our parabola that's opening downwards, and then we have the line at y equals 3, and we have our little enclosed region. And now again, we want to revolve that around the x-axis. So revolving around the x-axis, you can see now we got into two colors, our outside and our inside color as it kind of comes around. We're revolving it. And you can see now the 3D shape that we're kind of trying to make. If I move this way a little bit, you can kind of see down that side of it, but you can see we have a hole in the middle of it now, right? And then same thing if I swing this way. Try to swing it around here, but you kind of get an idea of what this is supposed to look like. Okay, you kind of see that washer now. Instead of having a solid disc in the middle, we've got this hole, so we kind of have this wash method. But this is the kind of shape we're going to try to find the volume of right here. All right? So I hope that helps make sense for you. Maybe one more time, revolving it a little quickly here. And I just think it helps if you can kind of picture what's going on, what you're trying to find the volume of. At least it always helped me in the beginning. This website I really like to kind of help me really grasp what we're going to try to do. But I can try to find the volume of that shape right there. All right? So now let's go back and let's talk about how we're going to do that. All right, so for the disk method, we had the area of this circle, right? And we integrated that from A to B, and we just did the area of the circle dx, right? That was disk method. For washer method, we're going to use a same side of idea, except for I need the area of like this donut shape now. And I'm going to integrate that from A to B. All right? So now how would we just find the area of this donut? And hopefully you're saying, hey, I would do, if I were going to do that, I'm going to do the, the big circle, area of the big circle, minus the area of the little circle. Or if I rewrite it differently, I could say that this is pi big R squared, big R for the big circle, capital R, minus pi little r circle, take away the area of the smaller circle. And that would give me the area of this washer, right? Or if I wanted to, I could even factor out that pi, big R squared minus little r squared, and that would give me the area of the washer as well. And that's why when we do this, our formula is pi big R squared minus little r squared dx. Again, where r is the function, right? R, in this case, r is going to be the outside function, and little r is the inside function. Or going back, we can always think top minus the bottom, right? That's how we're finding the area between curves, and that's essentially what we're doing here. So big R is the top function, little r is the bottom function. Okay, and now for our next example, we're going to try to find the volume when you take the area between y equals x cubed and y equals x squared and revolve that around the x-axis. So here I've got y equals x squared and y equals x cubed drawn, and we're going to revolve this now around the x-axis. Alright, and then I'm going to, real quick, I'll show you on the computer simulation. Okay, so here's our enclosed area. Y equals x squared and x cubed. And now if we revolve those, this is the function that we're going to get. Kind of, I don't know, top, maybe, the top of a circus tent, maybe, if you look at it like that direction. I don't know. Okay, but trying to give you an idea of what this thing looks like. But you can see we have open space in the middle down here. It's not completely full, so it kind of looks like that. That's what we're trying to find. Alright. Okay, so things that we need to do here. First, we need to figure out where these are going to intersect so that we know the limits of our integral. So, we're going to set these two functions equal to each other. X cubed equals x squared. Set it equal to 0. And we can see that this is going to intersect at x equals 0 and x equals 1. Alright, so now we know our limits. I'm going to go from 0 to 1. And now I need to just focus on what the big R is. Again, the big R goes from whatever you're revolving it around to the outside function, okay, or the top function. You always do top minus the bottom. So in this case, that is the top function right there. Now I guess the real question comes, well, what function was that? Well, if I put in a value between 0 and 1, like 1/2, if I square 1/2, I get 1/4. If I cube 1/2, I get 1/8. 1/4 is bigger than 1/8, therefore the x squared is the top function and the cubed is the bottom function. Alright? So pi r, big R, is going to be the x squared one, minus little r is the close one, it's going to be x cubed, dx. Okay, pi big R squared minus little r squared. And oops, I put my r's in, but I forgot to square them. Big R squared and little r squared. Okay, that's how we would set this up to do the washer method. So again, I would pull the pi out in front, simplify the inside, use reverse power rule, and now we're at 2 pi over 35 would be your answer when you did everything. Kind of going to skip over that just to keep things a little bit shorter here. One thing I did forget to mention, though, I think, is how do I know when to use, washer method versus disk method, right? And I know to use washer method when I have a gap between whatever I'm trying to revolve around, okay? So in this case here, we have this gap underneath our area, therefore that is a washer problem, okay? Going back one, right here we had this gap between our area and what we're trying to revolve around. So that's washer. If it is touching, our shape was touching, right? And here this one we had, looked like this. And so the shape was touching the whole way the x-axis. Therefore that is a disk method. The whole way here, right? So that is a disk method problem. So if you have a gap, you're going to use the washer method. If you have no gap, if it's touching the whole time, then you're going to use disk method. All right. Here's another one, and I'll let you tell me which method I should use. Okay. So here we're going to take y equals 6 minus 2x minus x squared, and the line y equals x plus 6 in the area enclosed by those. So this area right here, and I want to revolve that around the x-axis. So what method are we going to use? Hopefully you're saying, oh, this is going to be washer method. Again, we have this gap down here between our enclosed area and the x-axis, so this would be a washer method problem. All right? So now I need to do my a to b pi, and you can pull that out to begin with if you want to, big R squared minus little r squared dx. We're going to use this formula right here. So I'm first going to go find the limits from my integral, and so I do that by setting the equations equal to each other. And when I do this, I get x equals 0, -3, so that kind of corresponds with my picture here. And then now I need to set up my integral. So pi, -3 to 0, big R, again, is the top function or the outside function. which is 6 minus 2x minus x squared squared, minus the little r is x plus 6. Okay, big R all the way to the outside, that's the long one. Little r is on the inside. All right. When you're doing this, one of the most common things to forget is this squared up here. You notice I almost forgot on that last example, and then when I wrote this down, I almost forgot on this one again. Okay, so be careful. It's big R squared minus little r squared. Big R, little r. And I know this is kind of tough to see. You know, it kind of takes some practice setting these up, so make sure you practice this tonight. When I go and evaluate this now, you're going to get 243 pi over 5. Should be your answer. All right, one more little thing to show you. Okay, for this last example, we're dealing with the same graph here now. Y equals 6 minus 2x minus x squared, and y equals x plus 6. Except for now, instead of revolving it around the x-axis, we're going to revolve it around the line y equals 3, around a horizontal line. When you resolve a function around a horizontal line, we're going to use the same methods we use to revolve it around the x-axis. It is flat like the x-axis is flat, is the way I kind of think about it. All right? So, again, if I'm looking at this line here, I still have a gap between our shape and the line that I'm revolving around. Therefore, I need to use washer method. And in the last problem, we went and found out our limits. They're still going to be the same. I'm going to go from -3 to 0. Pi. It's just now that big R squared, instead of going all the way down to the x-axis, big R is only going to go to that line. And same thing then, little r is only going to, to that line. So, again, to get the length of that line, what you want to do is you are going to take your big R, the top function, 6 minus 2x minus x squared, and then you got to take away this distance of 3 is the way I think about it. Or again, top function minus that bottom function. Still use that as well. But that would become my big R. Same thing with little r. Minus little r is x plus 6. But then I got to take away that distance of 3. Minus 3 squared. And then again, don't forget your dx. All right? All right. We may have to talk about that one a little bit more live in person because I know these are a little bit confusing to set up. And I'll have to walk you through a few of those. But that would be the setup we would use. And again, when you evaluate this integral, you should get 108 pi over 5. And again, all these I'm just giving you answers to because I'm worrying about the setups of them. However, you should be able to evaluate all of these by hand. All right, boys and girls. That's it for this one. I will see you again real soon.